Welcome to the Year 10 exam marking video. This week's exam is on braking, reaction time and momentum. You need to make sure you have your blue pen and green pen. The green pen is for making corrections to your work and for ticking where correct. Your blue pen is for making annotations that are linked with the thought process that you should be going through when answering these questions. So let's get started. 1. Figure 1 shows the forces acting on a car moving at a constant speed. This is figure 1. Immediately I'm thinking the forces are balanced because the speed is constant. The question is asking which force would have to increase to make the car accelerate. In other words, speed up or increase in velocity. So to increase the velocity, the forward force must increase, so it must be C. And that is my answer. That gives you 1 mark. Question 1b. The car travels a distance of 2040 meters in 2 minutes. So underlining the values given, use the following equation to calculate the mean speed of the car. So you're given the equation, however, I've still followed the method here, listing my values, because the first thing I'm going to say is that speed, or the mean speed, is measured in meters per second. I know that because I'm told meters per second over here. So you need to convert the time from 2 minutes, multiply it by 60 to get 120 seconds. Once I've listed my values with their units, I write the formula, substitute, which gives me a mark, and then I write my final answer in, which is 17 meters per second. So a top tip there is to always check the units they give you already. Sometimes that gives you a clue as to whether or not you need to convert, in case you've forgotten the standard units for a formula. 1c. The car makes an emergency stop. Figure 2 shows the thinking distance and braking distance of the car. The thinking distance is 12 meters and the braking distance is 24 meters. Now, remember, this is how far the car travels when you see an obstacle and you think about pressing the brakes, and this is how far the car travels when applying the braking force. So, the stopping distance is the total, the sum of the thinking distance and the braking distance. So if you wrote thinking distance plus braking distance, you get a mark. If you just added the numbers together and wrote 36 meters, you also get a mark. 1d. The person driving the car is tired. Now immediately I'm thinking this will affect their reaction time, and therefore it will affect their their thinking distance. What effect will this have on the thinking and braking distance? Well, if you're tired, then your reaction time is going to be a longer reaction time, and therefore you'll travel a further distance. So your thinking distance will increase, but your braking distance doesn't depend on how tired you are, because the braking distance means when you hit those brakes, how does the distance change if you're tired? Well, if you hit the brakes, that's got nothing to do with whether you're tired or not, once you've already pressed them, so it stays the same. So what kind of things would affect the braking distance? Well, when you hit your brakes, there's a certain distance you will travel. That distance will be higher if the car and road conditions are different. So if your tires are very old and worn out, that could increase your braking distance. If it's icy, that could increase your braking distance. If it's wet on the road, that can increase your braking distance. And finally, if you're traveling at a higher speed, that will affect braking distance. But braking distance is not affected by tiredness, only thinking distances. Question 2. 4 students tested their reaction times using a computer program. When a green light appeared on the screen, the students had to press a key. So imagine a light appearing and you have to quickly press a key and react. Table 1 shows their results. So clearly there are 4 students who have taken this experiment and they've done it 3 times each, and then the mean has been calculated. What is meant by reaction time in this experiment? Well, it's the time it took from seeing the green light to pressing the key. You just had to write down exactly what the experiment was about. Boy 2 had an anomalous result in test 2. Suggest a reason why. Well, anomalous means something that does not fit the pattern, or is something that's very different from other repeats, if we're looking at the repeats. Now, it seems to be the case that boy 2, for test 2, it's a much higher, longer reaction time. Now, what would cause a longer reaction time? Well, that must be due to some sort of distraction, so he could have been distracted. And if you named a distraction, you could also earn yourself a mark. 2C. Give one conclusion that can be made from the results in table 1. So, if you look at the table, there's two potential conclusions you can make. The first one is to do with comparing boys and girls. On average, it seems that girls have a longer reaction time than the boys. So you could say the boys have a shorter reaction time than girls. Both those give you 1 mark. And the other thing you'll notice is that the reaction time improves with practice. What that means is test 1 was the slowest and test 2 got a bit faster, test 3 was even faster than that. And that's true for everyone. Everyone seems to speed up. So that's the second conclusion you can make. 2D. Suggest further evidence that you could collect to support your conclusion. Well, you can either have a larger sample size, because testing 4 students isn't really a lot, and you get that mark if you said boys have a shorter reaction time than girls. And if your conclusion was that reaction time improves with practice, then your further evidence must be to take more repeat readings per person. So if each person took more repeat readings, you could see that they got quicker and quicker each time. E. Reaction time is important at the start of the race. Table 2 shows the time taken by a boy to run different distances. So the 100-meter race was obviously much quicker than the 200 meters, which was much quicker than the 800-meter race. Reaction time is more important in a 100-meter race than in an 800-meter race. Explain why. So why is it important to react quickly in a short distance than in a long distance race? Well, as distance increases, reaction time will have less effect. That gives you 1 mark, because it is a smaller proportion of the total race time. That's your second mark. So why are these 2 marks given? Well, if you imagine 2 different races, let's imagine a 100-meter race and a 200-meter race, and they both, let's say we were slower in that race by 1 second. So we were slower by 1 second. Now if you look at in the first race, that's quite a big chunk of the entire race. It's just going to make a big difference. But in the 200-meter race, compared to the 100-meter race, 1 second is a much smaller chunk of time. So it will have less effect on the overall time. You can think of it as it's harder to make up that 1 second in a 100-meter race, whereas if you're 1 second behind in a 200-meter race, you have more opportunity to make up that time. So it's more important in the 100-meter race to have a fast reaction time. Question 3. An investigation was carried out to show how thinking distance, braking distance and stopping distance are affected by the speed of a car. Immediately I'm thinking distance plus braking distance is equal to stopping distance. The results are shown in the table. So again, I've just made a little note that these two added together, thinking and braking distance, equal the stopping distance, and I'm right. 6 and 6 is 12, 9 and 14 is 23, etc. And this is given for different speeds. So I understand the table before I'm going to move on. Using the results from the table, plot a graph of braking distance against speed. Draw a line of best fit through your points. Before you start plotting, I would, because there are so many different things, 4 different things on the table, you're only asked to plot 2, braking distance, speed. So I would just put a box around braking distance and speed so I know where to focus on when I'm trying to find my pairs of points to plot on the graph. The second tip I would give you is to look at your scale and make a note of how much each little box represents. On the y-axis, each little box represents 1 meter, and on the x-axis, every 2 little boxes represents 1 meter per second in speed. That will help you plot accurately. Then we read off our pairs of data and we plot them to produce a graph that looks like this. You get 1 mark for plotting these 4 points correctly. The second mark is for drawing a line of best fit. Now some of you will have drawn a smooth curve that goes through all the points like this. That would give you the second mark. Some of you might have drawn a straight line, but you'll notice that if you try and draw a straight line, you always miss out at least some of the points. So that can't really be right. You have to always ask yourself, would a curve work better or a straight line? But there's one more piece of evidence that tells me this is definitely a curve and it cannot be a straight line, and that is this. Even though it's not on the table, really we know if the speed was 0, the braking distance, what would it be? It would have to be 0 as well, because if your speed is 0, of course you're not going to have to brake. So we know that really 0, 0 is a point, we can be sure of it. And if I was to plot that point, then it would only make sense if my line of best fit was a curve, because that would match perfectly with the rest of my curve. If it was a straight line, it most certainly would not make any sense. So that proves to me that a curve is better than a line of best fit. So a top tip, always ask yourself, if there is no 0 point, if there is no value which says 0, 0, ask yourself, would it make sense for there to be a point which is 0, 0? So I've written here, this point we know is certainly true, 0, 0. It helps us decide to draw a curve instead of a straight line. 3a part II tells you to use your graph to determine the braking distance in meters when traveling at 22 meters per second. So I'm going to use my little key that I made earlier, and I know that I need to go 4 little boxes because I want to go from 20 to 22, and I'm going to draw a line all the way up to my curve and then across to the y-axis, and I know each little box is 1 meter, so I do 30, take away 1, I'm on 29 is your answer. If you did a straight line graph, as long as you did the method correctly and you didn't get 29, you can still get a mark, as long as you followed the method of drawing a line up and along and reading the graph off where the point hits the line. (3D). Right, this is asking you to look at the speed time graph for a car. Speed time graph is the same as a velocity time graph, so immediately in your head you should be thinking, what do I know about velocity time graphs? This will be useful. While travelling at a speed of 35 meters per second, the driver sees an obstacle on the road. So an obstacle is something has blocked the way, so therefore they need to slam on their brakes. In the road at the time t equals 0, so that means when time is 0 on the graph. So if you look at where time is 0, time in seconds is 0, this is when he slams the brakes. The driver reacts and brakes to a stop. So first they react, and so the speed does not change because it takes time for you to react and press the brake. Then his foot probably hit the brake and the car started to slow down to 0 meters per second. So this part of the graph represents thinking distance, and this part represents the braking. What is the braking distance is the question. Now, to calculate distance in a velocity time graph, you need to find the area under the graph. But it's not the entire area, it's only the braking distance, which is when the velocity starts to change. So I'm only interested in finding the area of this. This is my braking distance. If I wanted to find the thinking distance, I would find the area underneath the graph where his speed does not change, but it's after when he reacted and slammed his brakes, which is at t equals 0. Or just before he slammed his brakes and he saw the obstacle. So the area under the graph is half times base times height. Now your base of the triangle goes from 0.6 seconds to 4.6 seconds. So I'm going to do 4.6 take away 0.6 to find how long this line is. And my height is all the way from 0 to 35 meters per second. So I'm going to do 35 take away 0 to get my final answer, which I have my substitution half times 4 times 35 equals 70 meters. If you got this line of working out, you get 2 marks, you get 1 mark for your final answer. If you got it wrong and you didn't get the correct substitution here, you can still get 1 mark if you tried to find the area under the graph of the triangle. Okay, the last question, question 4, is on of a glider on an air track. So, figure 1 shows the apparatus. Now remember, we looked at this as a demonstration last year. There's an air track which blows air, allowing the glider to smoothly, without any friction or resistance, travel along the air track. The speed of the glider is the same at both ends of the air track. That tells you it doesn't slow down. Now we can see there's a piece of card which moves through a data logger, which moves through the light gates, which is connected to a data logger. When the card goes through, it records how long the card is blocking the light gate for, and it uses that to work out the speed. What is the tendency for objects to continue at the same speed in the same direction called? Now, you should know this is called inertia. If you didn't come across this term, this is your opportunity to learn the definition now. 4b. The glider has a mass of 0.14 kilograms and a velocity of 17 centimeters per second. Calculate the momentum of the glider. Now you should recall from your work on this topic that momentum, we use the symbol rho, which is the Greek letter, but we can just call it P to make it easier. P is equal to kilogram meters per second. We know momentum is measured in kilogram meters per second. It also tells you here. We know that the mass is 0.14 kilograms. The velocity is 17 centimeters per second. However, we need to convert this into meters per second, and in order to do that, we do the following calculation. We know that 1 meter equals 100 centimeters. We want to go from centimeters to meters, so we need to go from 100 to 1, so we know that we need to divide by 100. So 17 divided by 100 is 0.17 meters per second. We then write the formula, momentum equals mass times velocity. Momentum equals 0.14 times 0.17, substituting in those values. You should have got 0.0238 kilogram meters per second. However, because we are given the mass and velocity to 2 significant figures, we must round to 2 significant figures to give us 0.024 kilogram meters per second. So give yourself 3 marks if you got that. Give yourself 1 mark if you have this substitution in, and give yourself 1 extra mark if you got this. So 1, 2, 3 marks. The next question is about momentum again. This time we've got 2 identical gliders traveling at the same speed in opposite directions. So we're not told the speed, we're not told the momentum or anything, but we're just asked to think about it generally. Identical gliders have the same mass, they have the same shape, so they'll behave similarly. Now what I've done to help myself imagine this is just give random numbers onto this problem. So let's imagine this is 1 kilogram glider and it's going at 3 meters per second. The momentum will be 3 kilogram meters per second. The other one is going in the opposite direction, but it's identical, so it's also 1 kilogram, but it is traveling at -3 meters per second because it is traveling in the opposite direction. So whilst the first glider's momentum is 3 kilogram meters per second, the other one has a momentum of -3 kilogram meters per second. So that's what we should be imagining. Because the question says the gliders collide and stick together. Explain what happens to the momentum and speed of the gliders. Now, we know the total momentum before the collision is 0 because they are going at the same speed, they are the same mass, but they're travelling in opposite directions. So the total momentum is 3 plus negative 3, 0 kilograms meters per second. If you said that, you get 1 mark. The second mark is just saying after a collision, momentum is conserved. That is a rule. So whenever you're asked a question about changes in momentum, it's a good idea to always write this down. You're likely to get a mark. After a collision, momentum is conserved. So the total momentum after the collision is, it should be 0, because before it was 0, after it should be 0. So you get another third mark for saying that. Finally, you get a mark for commenting on the speed of the gliders. When they meet and they crash, they're going to come to a standstill, because then the momentum will be 0. Because if v is 0, then momentum will also be 0. So the final markers are saying the speed after the collision is 0. The final question is about the light gate shown in figure 3. It aims a beam of light at a sensor. So let's see what's going on here. Here is the beam of light. It hits the sensor. But when there's a piece of card in the way, the beam of light stops hitting the sensor. The data logger calculates the speed of the glider. Now we can already imagine how this might work. The data logger divides the length of card by the time for which the card breaks the beam of light. So length of card we can think of as distance, and time is we do distance divided by time, and that will tell you the speed. So if we know how long the card is, fixed card length, and we know how long it breaks the beam of light for, then we can work out its speed. Now that's interesting, because figure 4 looks at a similar concept but with vehicles on the road. But I'm already thinking in my head there's a problem here, because here there's one thing that breaks the beam of light, the one piece of card, and we know its length. These cars are next to each other, so how is that going to work? We won't know if there's a second car there, if there's another car in the way. And secondly, we don't necessarily know the length of the cars. And that's the answer to the final question, which says the beam of light and sensor shown in figure 4 are not suitable for determining the speed of vehicles on the road. Give 2 reasons why they are not suitable. So an explanation would be, and so you need to give 1 reason, 1 explanation, another reason, another explanation. So the reason 1 is more than 1 car may pass through the beam at a time. Explanation is that the light gate cannot accurately measure the time for 1 car to pass if they're 2 together. The second reason is cars come in different lengths, and the explanation is speed cannot be calculated without the length. Okay, once you've done that, you need to add up the total number of marks you got, and it's a good idea to write your marks at the top, what you got out of 30. Remember, what's more important than getting full marks is to make sure you've annotated correctly where you have missed the marks, so that in future, in a real exam, you're more confident going in, you know exactly where you've gone wrong. This is a reminder of the homework that's due in on Monday, these 3 bits of homework.